Hello everyone, welcome to Brain Blitz Audios. In this episode of Mind Maps, we'll be dealing with the 8th chapter in the physics syllabus of grade 12 CBSE. The chapter that we are dealing with is Electromagnetic Waves. And as always, we'll be enlisting the help of a mind map to run through this chapter. Mind maps are really easy tools for last-minute revision. However, sometimes they can be pretty extensive, and therefore this video is devoted to explaining this mind map in some detail. We'll be covering this mind map in 8 steps. Phase 1 would look at the general overview of the chapter. Phase 2 will look at the characteristics of electromagnetic waves. Phase 3 will look at the history of electromagnetic waves. Phase 4 and 5 will deal with conduction and displacement current respectively. Phase 6 will look at James Clerk Maxwell's 4 equations with regards to electromagnetic waves. Phase 7 would look at energy density, and the last phase, 8, would look at the electromagnetic spectrum. So let's move on to our first stage, electromagnetic waves. Electromagnetic waves are the waves which are related to both electricity and magnetism. These are the waves which are coupled with time-varying electric and magnetic fields, and they propagate in space. The formula for electromagnetic waves are time-varying electric field plus time-varying magnetic field is electromagnetic waves. So these are a combination of mutually perpendicular electric and magnetic fields. So these are some of the So we'll be dealing with characteristics, energy density, electromagnetic spectrum, displacement current, conduction current, history, and Maxwell's equation. So these are all the part of the chapter with which we'll be dealing with regards to electromagnetic waves. So these are all related to electromagnetic waves. So moving on from electromagnetic waves to characteristics of electromagnetic waves. So these are some characteristics of electromagnetic waves. The first one states that electromagnetic waves do not need any material medium for propagation. So what this means is that unlike sound, which requires air, water, or solid to move through, electromagnetic waves do not require a medium. Now, earlier scientists who are familiar with sound made a proposition that the whole universe was made of ether, and this ether was the medium for conducting light and electromagnetic waves. However, this was later disproved, and now we know that electromagnetic waves do not need any material medium for propagation. Light can pass through vacuum as well. The next characteristic states that electromagnetic waves travels with the speed of light. Now this was proved by Heinrich Hertz, and he propagated the formula for speed of light based on the electric and magnetic fields. So the formula is C is equal to 1 by root of mu naught times epsilon naught. So mu naught refers to permeability and epsilon naught refers to permittivity. Now both of these are constants in magnetic and electric fields respectively. Right, so let's look at the next characteristic. Electromagnetic waves are produced by accelerated charged particles. Now, how do we find out whether an electromagnetic wave is produced by a charged particle? So let's rub all of this. There we go. So let's look at an oscillating particle. So this particle here is oscillating between points A and B. So it's moving from A and it's coming back to B, and it's doing that motion over and over again. So this is a charged particle that is undergoing oscillatory motion. And if you've studied the second chapter, we would know that it creates an electric field, E. But that electric field, in turn, would create another magnetic field, B. And then that magnetic field would go on to create another electric field, E bar, and the cycle goes on, eventually creating electromagnetic waves. So that's how electromagnetic radiation is created. It is by the overlapping of electric and magnetic fields. The next property says that electromagnetic waves are transverse in nature. Now, transverse waves are those in which the direction of disturbance or displacement in the medium is perpendicular to that of the propagation of the wave. So what happens here is that a particle, it moves up and down, and the wave that forms due to this motion is moving in this way. So as you can see, the direction of the motion of the particle is perpendicular to the direction of propagation of the electromagnetic wave. So particles can move up and down. And so that's how electric fields and magnetic fields are made. And electric fields and magnetic fields are perpendicular to each other. And they're also perpendicular to the medium. And they're also perpendicular to the traveling direction. So as you can see, this is the electric field. It's perpendicular to the traveling direction. And that is a similar story for the magnetic field. And all of these are represented on separate axes. Moving on to our last and final characteristic, oscillating electric and magnetic fields are in phase and their ratio is constant. And the ratio is C is equal to E naught by B naught. E naught is electric field and B naught is magnetic field. So what this says is that the electric and magnetic fields are in phase. So angular displacement phi is equal to 0. So if you see the graph for electromagnetic waves, you'll notice that at E naught is equal to 0, the value of B naught is also 0. And as it moves on increasing, the magnetic field also increases. And when the electric field decreases, the magnetic field also decreases. There is no phase difference in between electric and magnetic fields. So that's the overview of characteristics of electromagnetic waves. Now let's move on to the history of electromagnetic waves. In 1886, Heinrich Hertz became the first person to transmit and receive controlled radio waves. Now he proved Maxwell's studies on electromagnetism, and he proved that light is an electromagnetic wave through this experiment. He also calculated the speed of an electromagnetic wave, which is equal to the speed of light. And in India, J.C. Bose undertook a similar experiment, while Marconi went on to create wireless communication through the radio. And through that, electromagnetic waves have become a pivotal part of today's communication and entertainment. And so in order to honor Heinrich Hertz, the SI unit of frequency is named Hertz, or Hz. So that's all about the history of electromagnetic waves. Now, before the advent of electromagnetic waves, we never distinguished between conduction and displacement current. So the advent of conduction and displacement current were direct results of electromagnetic waves through the research of James Clerk Maxwell. So let's look in detail about what conduction current and displacement current actually mean. So conduction current. So conduction current is the current which is arising due to the flow of charges. So you have a conductor and there's a flow of charge Q in time t. Then the quantity used to represent that is known as conduction current. Conduction current is represented as IC. And the formula for IC is dq by dt. dq is change in charge, divided by dt is change in time. And so since the values are infinitesimally small, we use differentiation to get this formula. So IC is equal to dq divided by dt. Now this kind of current was the one which we studied in the third chapter, current electricity. And for a long time, the definition of current in general was the definition given to conduction current. However, Maxwell's studies have put forth a new kind of current, that is displacement current. Now, in displacement current, the current arises due to the change in electric field. Change in electric field. So it is denoted by ID, that is displacement current. And the formula for displacement current is E naught times minus d phi E by dt, where E naught is permittivity of free space and d phi E divided by dt refers to electric flux. So the displacement current is represented as the product of permittivity of free space and electric flux. So that is why it is known as the current which is arising out of a change in electric field. Now, Maxwell got his research due to his experiments in a capacitor. So in a capacitor, the current that flows through the wires is IC, conduction current, while the current that flows through the capacitor here, so in between the plates we have electric field E. So then the change in electric field E gives you the displacement current, ID. So ID is present in between the plates of a capacitor, and IC is present through the wires that lead to the capacitor. And the thing to note is that the physical behavior of both displacement current and conduction current are one and the same. And to find out the total current in any system, we just add conduction current and displacement current. And through Maxwell's research in capacitors, he understood that displacement current was the missing term in Ampere's law. So while he was studying Ampere's law, he put forward the hypothesis that an electric field creates a magnetic field, and a magnetic field gives rise to an electric field. However, in specific situations of Ampere's law in a capacitor, he found that the magnetic field and the electric field both equated to 0. And that was because they only used conduction current at the time. But however, with the advent of displacement current, the magnetic field and electric field were duly calculated. And so now they lead on to our next segment, Maxwell's equations. Maxwell gave a set of 4 equations which are known as Maxwell's equations. These equations describe how an electric field can generate a magnetic field and vice versa. So they describe the relationship and behavior of electric and magnetic fields. So E and B. A flow of electric current will generate a magnetic field, and if the current varies with time, magnetic field will also give rise to an electric field. So we have 4 Maxwell's equations. The first equation is Gauss's law in electrostatics, and this describes the surface integral of electric field. So integral ds gives the surface integral, and ds represents surface area, which is small, and E stands for electric field. So integral E dot ds as a whole represented induced EMF. And so that is equal to Q, induced charge, divided by E naught, which is permittivity. The second equation is Gauss's law in magnetism, and it describes the surface integral of magnetic field. So magnetic field times the small surface area gives you the surface integral of magnetic field, and it is 0 always. The third law is Faraday's law, and it describes the line integral of electric field. As you can see, the formula is closed integral E dot dl, and dl represents small part of a line. So basically line integral. So integral dl is line integral, and E represents electric field. And the line integral of electric field is given as minus d phi b by dt. And so this quantity is known as the magnetic flux. And then we move on to the last law, the Ampere's law, which describes the line integral of magnetic field. Now, this is not the original Ampere's law. The law here is known as Ampere-Maxwell law, because Maxwell, after finding changes in the original Ampere's law, made this formula and corrected it. So again, magnetic field into the closed integral of a small part of a line would give you the line integral of magnetic field, and that is equal to mu naught, which is permeability, times current. And so here, instead of just current I, he used both types of current, conduction current and displacement current separately. So this is conduction, IC, and E naught minus dE by dt gives ID. So closed integral B dot dl bar is equal to mu naught times IC plus ID. So that is the main change used by Maxwell. So instead of keeping current as just one, he made it into two. So the current in the capacitor would contain both conduction and displacement current, and he multiplied them separately using the distributive property and put the values for both to get the equation mu naught I plus mu naught epsilon naught minus d phi e by dt. And that's all about Maxwell's equations. Let's look now at another important topic, energy density. Energy density is the total energy stored per unit volume. And so to find the energy density of an electromagnetic wave, we find the energy density of, let's represent it as U. So energy density will be equal to U of electric field, that is the energy density of electric field, plus the energy density of the magnetic field. So the energy density of an electromagnetic wave is given as the component of the energy density of both its electric and magnetic fields. So now we add these two to get the final result. And so the formula for energy density for an electromagnetic wave is half E naught E square plus half B square by mu naught. So half E naught E square would represent UE, and half B square by mu naught would represent UB. Now, to find the average energy density over a long period of time, we use the same formula. But the catch is that since the time period is given as a long time, the average energy density can be reduced to its individual components. So U average is equal to half E naught square epsilon naught, and it is also equal to half B naught square divided by mu naught. So that is about energy density. So it is the total energy stored per unit volume, and it's calculated as the sum of the energy density components of the electric field and the magnetic field, and the average density can then be reduced to individual energy densities. And so now we've reached the final part of this chapter, the electromagnetic spectrum. So the spectrum here shows the wide variety of electromagnetic waves known to us. So this is the spectrum. So it ranges from long wavelengths to short wavelengths. Let's look at each of these one by one. The electromagnetic waves with the longest wavelength are radio waves. So these have wavelengths which are greater than 10 raised to 8 nanometers or 0.1 meters. And radio waves are having low energy, and they have the largest wavelength, and they are used in radios and TV signals. Now, immediately succeeding radio waves are microwaves. Now, these are the waves that are found in your microwave oven, and they range from 10 raised to 8 to 10 raised to 5 nanometers. And so these have higher frequency, lower wavelength, and higher energy than radio waves. Microwaves were initially used in radar, and from there they found their way into our homes in microwave ovens. The next type of radiation is infrared radiation, or IR. Now, the wavelength of this ranges from 10 raised to 5 to 700 nanometers. So it's a very wide range of radiation, and it's primarily used in night vision. So night vision cameras use IR. IR is also used in physical therapies and TV remotes. And infrared radiation is hard to be seen with the naked eye, but if you use the camera of your smartphone, you'll be able to see a reddish light coming out of your remote when you click a button. That is infrared radiation. Try it out. From IR, we move on to visible light. Visible light is the light that humans can see, and the wavelength ranges from 700 to 400 nanometers. 700 is red and 400 is violet. So 700, 400. And so blue is 450, green is 500, yellow is 550, 600, 650, and 700. So visible light is the kind of electromagnetic radiation that we can see, we humans can see. The term visible light may vary for insects and others because some insects can see ultraviolet radiations and some other animals can see infrared radiation. So when we talk about visible light, we're talking about visible light for humans, and that ranges from 700 to 400 nanometers. These are used for seeing the various objects around us. And from visible light, we move on to radiation with stronger side effects such as UV rays. So UV rays have low wavelengths ranging from 400 to 10 nanometers. So these have low wavelengths, but because they have low wavelengths, they have higher energy. So the formula here is wavelength is inversely proportional to energy, and it's also inversely proportional to frequency. So since UV rays have lower wavelength, they have higher energy. UV rays are used for destroying bacteria in water, so they're an important step in water purification. And since they're very powerful, they can be harmful to life on Earth. So the Earth itself is protected by an ozone layer, which has been decreasing and deteriorating sadly, and it's a cause for international concern because of the fact that UV rays can penetrate through our skin and damage our DNA. So before we move any further, let's erase all the ink in this slide. And from UV rays, we move on to X-rays. X-rays are more powerful than UV rays, and they are shorter. Their wavelength ranges from 10 to 0.01 nanometers. And X-rays are used to detect bone breaks and other medical diagnosis. And they're also used to treat some cancers. So X-rays are really powerful, and therefore their use is judiciously confined. And from X-rays, we move on to the most powerful radiation of the electromagnetic spectrum, gamma rays. Now, these gamma rays have a wavelength less than 0.01 nanometers, and therefore they have the highest energy. They're primarily used to treat cancer in chemotherapy, and these are also present in nuclear explosions. So therefore, they are extremely powerful, they have an extreme penetrating capacity, and they are harmful for all forms of life. Now note that in the electromagnetic spectrum, we talked about limits such as 10 raised to 8, 10 raised to 5, 10, 700, 400, 10 nanometers, etc. But these values are not rigid. the limits can overlap, and they do overlap. So it does not necessarily mean that a microwave has to be strictly between 10 raised to 8 and 10 raised to 5. It can also range at some values greater than 10 raised to 8 or lower than 10 raised to 5. So the wavelength of the electromagnetic spectrum is fluid and not rigid. And so that's all about the chapter Electromagnetic Waves. We looked at its characteristics, its history, the different types of current present due to electromagnetic waves, Maxwell's equations, energy density, and electromagnetic spectrum. So that completes the chapter Electromagnetic Waves. And did you know that Brain Blitz Audios is specializing in providing free educational content to all? To be a part of our journey, please subscribe to our channel. Please hit the notifications button to receive more updates about our useful and interesting content. Until the next episode, see you soon. Bye-bye.